Hello, Algebra 2 people, and welcome to our next video on probability of multiple events. Last week, some of you became slackers. We had a test that was due Wednesday, and some people still aren't done with it. Make sure you're getting that done. And then we had another assignment that was due on Friday, so some of you are 2 assignments behind and really need to get with it. I don't want to see any of you back in my classroom next year because you decided to fail math and now won't graduate on time unless you take me again. So just go, get on it. In the meantime, the last time that we had a video, we were talking about the probability that something was going to happen. And we're going to carry that one step further and talk about what's the probability of multiple events happening. So, for example, I could flip a coin, and that's one event, and then I could roll a die, and that's a second event. And those two would be considered what's called mutually exclusive. That means that one doesn't have any effect on the other. And so when you're looking at the probability that some things happen that are exclusive events, we could say, what's the probability that we can get like a head and the number 3 on a number cube or a die. So the probability that event A happens and the probability that event B happens is you're just going to multiply those together. So you say, well, the probability, for example, if the probability A was that I was going to flip a coin and get a head, well, the probability that I could get a head on a coin flip is 1 out of 2. Again, because it's what we're looking for, the head, that's one side of the coin, over the total amount that could happen. There's 2 sides of the coin. So one side is heads, 2 sides to the coin. So that's a 1 out of 2 probability. And then if we look at the probability of B as the probability that we'll roll a 3 on a number cube or a die, how many 3s are on that cube? Well, there's 1 3, and there are 6 total possibilities because there's 6 numbers on that die. So the probability that I would roll the die and get a 3 and flip the coin and get a heads would be 1/2 times 1/6, and that's going to be 1/12. So the probability that we'll, in this arrangement, that we're going to have a flip of a coin and the roll of a die, the probability that I'd get a head and a number 3 come up on the die is 1/12. Okay? On page 600, I turned to the page. On page 689 of your textbook, if you want to look at some examples there, there's some pretty good stuff, and it explains what mutually exclusive kind of means. Sometimes we have non-mutually exclusive events, and mutually exclusive, again, means that one doesn't have anything to do with the other. But suppose that we go back to our idea of marbles in a bag. Suppose that I have white marbles and blue marbles in a bag, and maybe there's 6 and 4. So maybe for my blue marbles, there's 6, and for my white marbles, there's 4 inside a bag. And so there's a total of 10. And so you go, well, what's the probability then that I would pull out a white marble and then I pull out a blue marble? Okay, in that order, what's the probability that's going to happen? Well, if I was going to pull out a white one first, there's 10 total, so the probability, that first probability, is going to be 4 out of 10, right? The probability that I pull a white marble out first. And then what's the probability of pulling out a blue marble? Well, these are not mutually exclusive events, because if I pulled out the white marble and I set it to the side, then that has an effect on the probability for the second time I reach into the bag, because no longer are there going to be 10 marbles in the bag, but now there are only going to be 9 marbles in the bag. So that changes the probability the second time around. If I'm pulling out a white one, the probability is 4 out of 10, but now after that happens, if I try to pull out a blue marble, there's still 6 in there, and there's only 9 total. So that second event has changed a little bit because of the first event. They're no longer mutually exclusive, but the first event had an impact on the second one. And so that's important to understand when we're talking about probability of events. Sometimes there's no relation between the two events, and sometimes there is a relation between the two events. But if I'm going to talk about the and happening, that I'm going to pull out a white one and then I'm going to pull out a blue one, I'm still going to multiply. So 4 times 6 here is going to be 24, and 10 times 9 is 90. Now, some of these had some common factors, and if we go back to our idea on fractions, 4 and 10 both had common factors of 2, so this really could have been 2/5. And 6 and 9 both had common factors of 3, so we could have taken out the 3 and gotten 2/3. And then when you multiply, you would get 4/15. Yep. So whether you do it this way and then reduce to get 4/15, or you do it this way and you get 4/15, the probability that you'll pull out a white marble and then a blue marble in that situation is 4/15. Okay. The second one that we want to talk about is an or, and I'll use a problem out of the book, I guess, because I'm not thinking of one off the top of my head. It says languages at your high school, a student can take one foreign language each term. About 37% of the students take Spanish and 15% take French. I know all you guys say, well, I want to take French, but then you don't know any French people, so why do you want to take French? But anyways, plus the French are rude. Sacre bleu. In your book on page 690, it says about 15% of the students take French. What's the probability that a student chosen at random is taking Spanish or French? And so we have an or situation. It's not an and. It's not like they couldn't take maybe both. But in this case, it says that they're taking one or the other. So what we're going to do is look for a probability of or. Now, turning back and forth in my book, because when we say or, it has a special meaning. Like when I say and, there's only one way to do that. It's kind of like you go, well, I want to buy some ice cream. If I say I want chocolate and vanilla, I can only accomplish that task if I do both. If I buy chocolate and I buy vanilla, right? But on the other hand, if I went to the store and I was going to buy some ice cream and I said, you know what, I feel like some ice cream, I think I'm going to get chocolate or vanilla. Either way, I could go in, and if I bought chocolate, that accomplishes the task. On the other hand, if I bought vanilla, that accomplished the task as well. So when we're talking about the difference between an and an or, you understand that and means that both of these things have to occur, or means that one or the other could occur. But there's a third possibility here. Suppose that I went into the store saying, you know, I think I'm like some ice cream. I'm going to buy either chocolate or vanilla, and then I couldn't make that decision in the store, so I came out with both chocolate and vanilla. And then my original statement is still true because I went in the store and said, I'm going to buy either chocolate or vanilla. And when I come out with both, that's still true. I bought chocolate or vanilla, even though I bought both of them. So there's these three cases. I could do A or I could do B, and that works fine. But what happens if I did A and B? And the solution to that's at the bottom of page 689. It says, what's the probability of doing A or B? And it says, well, what you have to do is you add the probabilities. So an OR is when you take the probability of A plus the probability of B, but then from that we'll subtract that we did both, the probability that it's A and B, that it's both of them. Hopefully that makes a little bit of sense, and we'll do this problem together. As it says, what's the probability of A? Well, if 37% of the students take Spanish, and I'm looking for the probability that students either take Spanish or French, I've got to take into the consideration that maybe somebody's taken both because they're just, I don't know, overachievers. They like foreign language. The probability of A in this case is 0.37. That's their 37% of the students that take Spanish. Then it said there were 15% of the students that took French. So if a probability of B was that they took French, then I would say 0.15. Once again, 15% is 0.15. But are they mutually exclusive? Oh, it does say they're mutually exclusive. In this case, they're not letting the students take both, so we'll just leave it as this first part. But if they were to allow them to have done both, we would have to take that into consideration as well. All right, so in this case, we're just going to add these together. 0.37 plus 0.15, that's going to give us 0. That's going to be a 5, got to carry 7 and 5 is 12, carry the 1 to get 0.55. Right? 12, not 15. Mr. Fokin can't add. 7 plus 5 is 12. Write down the 2, carry the 1. 2 plus 3 is 5. That's 0.52. All right. Let's take a look at how Manga High looks at this, because there's another idea that involves tree diagrams, and they're a good thing to look at as well. But probably easier, or just as easy to look at them on here. Move me out of the way so I can actually click on something. So again, we're going to start on the easy level and play. Here's our bag of marbles idea, right? A bag contains 7 red counters and 7 blue ones. If a red counter is removed and not replaced, what's the probability the next counter will be red? These aren't mutually exclusive. So, like, how many were in there to begin with? Well, there were 7 red ones and 7 blue ones. So the original marble bag, or the original bag, had 14 counters in them. But the red counter was removed. So there's no longer 14, but 13 left. So, this is the only one that's going to work. And one of them was red. So they started with 7, but we took that out. So there's only 6 left out of now not 14, but 6 plus 7 for 13. So there's 6 out of 13 left. Here's that tree diagram that I was kind of talking about before. And in this case, it's just showing that, there's a certain probability that you're going to win or certain probability you're going to lose. But in each of these branches, the big idea here is that they have to add to be 1. So I'm going to take my 0.75 here and put it there. 0.25 and 0.75 add to be 1. 0.85 goes with this 0.15, because if you added those together, you'd get 1. And finally, 0.4 and 0.6 have to add to be 1. So those are pretty simple to work out. There's a 100% chance. It's like you're either going to win or you're going to lose. There's a 100% chance that you're going to either win or lose. right? So that's why it adds to 1. 100% is 1. Over here, 0.5 goes with 0.5, so it's 50-50 there. Might win, might lose. But over here, it's 0.7 that you're going to lose, so that means it's 0.3 that you're going to win. Again, this number plus that number's got to add to 1, and that means that 0.6 and 0.4 have to go together because that also adds to 1. You can get your calculator out and do these. If you're not good with your stuff, you go do 0.2 times 0.8, and that's going to tell you get 0.16, so that goes here. You're going to do 0.6 times 0.9, you're going to give yourself 0.54, that goes right there. 0.7 plus 0.4, that's going to be 0.28 when you do it in your calculator, so we'll go with those. Again, you got to get to 1. What do you add to 2 sevens to get to 1? Well, hopefully you add 5 sevens, because if you had 7 sevens, that would be 1. 4 nines plus 5 ninths, because 4 ninths plus 5 ninths is 9 ninths, that's 1. And 1 half plus 1 half, if you put 2 halves together, you get a whole 1. What do you get when you take 0.5 times 0.8? Hopefully you get 0.4. What happens if you do 0.5 times 0.7? Hopefully you get 0.35. 0.7 times 0.6. Hopefully you get 0.42. Pete plays 2 games of tennis. We're going to use a tree diagram to figure out the probability he wins exactly 1 game. Now, here's a little bit of a tricky problem, and we got to think about our OR situation. Let me go back real quick and think about OR. How do we do ORs? We have to add the probabilities together, right? So here we go. One possibility, if he wins exactly 1 game, is that he wins the first one but loses the second. So that's our first probability. We got 0.9 times 0.1, and they tell us that's 0.09, but we're not quite done yet, because there's another way for him to win exactly 1 game, and that would be maybe he loses the first game but then wins the second game. So in the first situation, we're going to take 0.9 times 0.1 to get 0.09. But in the second situation, we could take 0.1 times 0.9 again to get 0.09. And if we added 0.09 to 0.09, do it in your calculator, 0.09 plus 0.09, you'll get 0.18. It's adding those probabilities together. So there's 2 cases we got to work through and add those together. A bag contains 12 yellow and 8 blue counters. What calculation is needed to work out the probability of picking 2 blue counters without replacement? Okay, so we're not putting them back in. So that would be if I took 12, right, and I added 8. 12 plus 8 is 20 total. So the probability that I could pick like a blue counter would be 8 out of 20, but I don't put it back. So now how many blues are left? Well, 1 less, so there's going to be 7, and 1 less than 20 as well because I didn't put it back, and so that's going to be 19. So it could be 8 20ths times 7 19ths, right? Pete plays 2 games of tennis. The probability that he wins each game is 0.5. Well, that's nice. Use a tree diagram to find the probability that he wins exactly 1 game. Once again, we've got to look at the different probabilities that this could happen. So 0.5, he won that game, but then he's got a 0.5, he's going to lose the next game. So if you take 0.5 times 0.5, you're going to get 0.25. But there's another option. He may have lost the first game, but then won the second game. So we're going to take this 0.5 times that 0.5, and again, we get 0.25. Now, if we add those together, because it's an OR, if we add 0.25 and 0.25, we'll get 0.5. Complete the tree diagram. All right. the probability of a win-win has got to be 0.1. So I guess I have to take 0.1 and divide by 0.5. Because 0.5 times whatever this was would have given us 0.1. So if I go reverse and I divide, if I take 0.1 and I divide by 5, I get 0.2. So that's got to go there. Down here it says the probability that you're going to lose. Well, there's a 0.4 here. So let's see. 0.2 has got to be a 0.8 because these add to be 1. And then 0.8 times 0.4 is going to be 0.32. So the probability that you're a loser is 0.32. All right. Give these a try. Remember that if you're seeing if both events happen, you're just going to multiply. But if there's an or involved, like there were in those trees, you could say, he could win a game and then lose a game. So you're going to multiply because that's an and. You win and then you lose. Or you might like lose and then win. Remember that or, so that's why you're adding those probabilities together in some of those problems. Okay? Good luck. There will be 2 assignments this week, so make sure you're doing both. Don't give up now. You're here till the 15th. It would be a shame to fail the class and have to take stuff over next year because you put some work out in this year. You might as well take advantage of the work you did and make sure you're getting your stuff in and get it in on time, please. Okay? It's not vacation. It's school. Good luck to you. Hopefully we'll see you real soon. If you're doing your work, hey, great. You guys, some of you are doing great. Others, pick it up a little bit. All right. Thanks. We'll talk to you soon. Bye.